So I told you that a rocket will behave like a second order system. It'll be nice for the following 3 videos, which I'm gonna be discussing. Well, actually, for the rest of the stability videos, the analytical study, it's gonna be nice if you know about control theory. It isn't mandatory. Oops. But it's gonna help a lot. It's gonna help you a lot to understand the concepts I'm gonna discuss. A book I recommend is a book from Ogata. You don't have to read it all, but you know it's a good reference. All right, so I told you before that the rocket behaves out like a second order system. So what is a second order system? Well, I'm going to use the analogy of a mechanical second order system. It's going to be easy for you to relate it. So if we have a damper which dampens the movement of the mass m in such way that the force it dampens is minus we'll call it b times the velocity, and then the spring, well, it does let's say restoring force of minus k to x, and x is just the displacement, the linear displacement, the displacement that we move the mass m. So if we just do Newton's law, it's going to be forces are equal to mass x second derivative. By the way, for velocity we might as well just put the first derivative of x here directly. Well, there can be an external force that's just nudging this mass. So there's an external force, okay. And then there are the restoring forces that will try to push back against this external force. So they are the spring and the damper. Remember, we have a very similar equation for our rocket. If you recall, we have some terms that go with alpha, and sometimes that go with alpha dot, and then here instead of mass we have the moment of inertia. So it's similar to this. So this equation, if you solve it for x, of course the response. So the response is how x evolves with time. Okay, so obviously the response is going to be a function of the force. Imagine if we just put a constant force of whatever 10 newtons. So imagine we have, if we apply a constant force here, how's x going to respond? Well, it's going to be something like this, and it's going to dampen out. So it's going to move, and then it's just going to stay there at a point in which the external force is compensated by the spring. Okay, and what the damper does is, will basically dampen out this oscillation until the spring force is equal to the external force. So we have something similar in our rocket. All right. and it's going to move in the same fashion. For example, in this case, if we just gave it a kick, and then it's just like an impulse force, it's going to do something like this. Okay, and then it's going to tend to x equals 0, because there are no longer any external force. So this is a good analogy of how the rocket behaves. It's similar to this, but in angular motion. Okay. So what we have is, our equation is the sum of the moments are equal to moment of inertia times the angular acceleration. All the equations come from here. The equations we've been discussing. Okay. So if we open this up, we discussed that we had some terms that were proportional to alpha. So this is, and then some terms that were proportional to the first derivative. All right. And then we have the external force, external moment. I didn't talk about the external moment until now. I should put a minus here, because the corrective moment is going to fight against the external moment. On the other side we have this. Cool. And then we might as well just put instead of, let's put it correctly. This is the corrective moment, which is which goes with the alpha term, and then the damping moment goes with the angular velocity. So let's put md. All right. If we put everything on the other side, we have this. So let's put here, this is the external moment we put on the system. So it's the moment that we're forcing our rocket. Okay. And on the other side, well, we have alpha times the corrective moment plus alpha dot the damping moment plus this. Okay. So now we could take the Laplacian, well, the Laplace transform, sorry, not the Laplacian. Again, check control theory. It isn't, it's going to be easier for you to follow all this, but so if we take the Laplace transform, now we're going to have the external moment, but on s variable. Okay. Then an s comes out of the derivative, and then an s square comes out of here. I'm just going to go really quickly through this. You should be familiar with control theory if you want to properly understand this. But so yeah, I'm just going to go quickly through this. So the transfer function between the output, our output is the angle of attack, and our input is the external moment, is 1 over is squared times the damping moment plus the corrective moment. By the way, it's the first time I talk about damping moment and corrective moment, but it's the values. You just can check the the past video. I think the difference here is that I put the dynamic pressure and the reference area over here, over the other side. So along with alpha, we didn't have a corrective moment, but we had something like yeah, it's just the equivalent. Just we just multiplied or divided by the dynamic pressure and the reference area, but it's the same. All right. So the generic transfer function for a second order system is the following: is k natural frequency squared, and can't do lines, and dividing, well, we have s squared plus 2 damping ratio, natural frequency, and right, just recall that all second order systems are defined only by 3 variables: the gain, static gain, normal frequency, oh, terrible, and damping ratio. All right. So what are these 3 values on our system, on our rocket? Well, the static gain is 1 over the corrective moment. Let's see, the natural frequency is then going to be the corrective moment over the moment of inertia, and the damping ratio is the damping moment All right, so these 3 factors define how our response is going to be. This means if we know these 3 variables for our rocket, we can perfectly describe how it's going to oscillate, how the stability is going to be like, let's say, for any kind of input. So, for example, if this is a rocket. No, we're starting with a vertical rocket. Imagine we have a vertical rocket, and I just gave it a nudge. Okay, I just gave it an impulse, external moment, just a quick impulse. So if it had high damping, alpha in front of time would look like this. It would gain angle of attack at the beginning, so it will slightly go to one side, and then it will stabilize. That's a damped system. Our rocket is not damped at all, so as I discussed before, and we're going to see it later when we substitute our variables in these 3 key variables. So what we're going to do next is well, not next, but we're going to do it in future videos. We're going to substitute our damping moment and our corrective moments, or our values, to see, to get a feeling of what these variables are going to be like. And we're going to see that damping is going to be really, really low, around 0.05 to 0.07. For normal rockets, maybe model rockets can go higher, up to 0.2, 0.3, but yeah, it's not so common. So if we have an undamped, it's certainly always undamped. If we have an undamped system, this would be like critically damped or overdamped. If we have an undamped system, it's going to oscillate. Okay? This is undamped. And our rocket is going to do that. If we give it a nudge, it's going to oscillate. And if it's very, very, very undamped, well, it's going to oscillate. It's going to take a lot of time. It's going to take a lot of time to stabilize. Okay, we're going to take a look into this in the next video. But yeah, we can see two types of response. There's a transient response to perturbation. So this would be the transient. So we give the rocket a nudge, an external moment, and until it stabilizes, well, this is the transient. Okay. But then if we have an external moment that is persistent, like a sinusoidal, imagine an external moment that is sinusoidal, and well, the rocket is never going to stabilize. So in this case, we're more interested in the steady response. So not this part of the response. So not maybe the initial seconds, but how the rocket is gonna react after a few seconds when alpha doesn't depend on time. So first we're going to check this, the transient response, and then we're going to check the steady.